Earth's orbit is currently populated by over 30,000 tracked fragments of debris, moving at velocities exceeding 7 kilometers per second. Every spacecraft operating in this environment faces a hard limit on its lifespan, dictated by finite fuel reserves and the steady mechanical degradation of its components. In space, a minor anomaly, like a burst of radiation flipping a control bit or a single jammed mechanism, can instantly render a multi-million-dollar asset completely useless. This is the traditional closed system engineering model. Satellites are built as immutable, one-way systems, destined to be discarded once they reach their inevitable failure point. Without a method for robotic intervention, this static design philosophy converts highly valuable orbital paths into an expanding, hazardous graveyard. On-orbit servicing represents the departure from disposable space hardware. It is the transition toward treating satellites as maintainable assets rather than one-shot electronics. OOS capabilities allow a servicer vehicle to intercept a satellite, replenish its propellant, robotically swap out failed components, or physically push it into a new orbit without ever returning to Earth. Northrop Grumman validated the commercial viability of this approach with their MEV-1 mission, successfully docking with and extending the life of the Intelsat 901 satellite. Executing a servicing mission requires mastering 3 distinct pillars: autonomous rendezvous algorithms, extreme environment robotics, and high-fidelity ground control links. The core engineering challenge is a paradox. We have to perform delicate, millimeter-precision mechanical repairs inside an inherently violent and hostile vacuum. The operation begins with autonomous rendezvous and docking, or AR&D. The immediate obstacle is that most defunct satellites are uncooperative targets. They were never designed to be serviced, lacking standardized docking plates or visual tracking markers. Navigating safely toward a potentially tumbling, uncooperative object requires a highly calibrated, layered sensor suite. The sequence starts with LiDAR. By bouncing lasers off the target, the servicer calculates distance, relative velocity, and the raw geometry of the object from miles away. As the servicer enters the close proximity operations phase, it switches from LiDAR to optical cameras for the final approach. Onboard AI and computer vision neural networks process this optical data in real time, actively identifying specific structural features that a robot can safely grab. Closing the final meters at orbital velocities is too fast for manual control. Securing millimeter precision relies entirely on autonomous AI. Once the target is secured, the physical capture phase relies on multi-degree of freedom robotic manipulation systems. These exposed mechanical joints must operate flawlessly as the spacecraft rapidly moves in and out of Earth's shadow. This visual highlights the resulting thermal shock. Surface temperatures on the arm swing from negative 150 degrees to positive 150 degrees Celsius in a matter of minutes. Combine that with high radiation conditions, and the robotic arm's internal control electronics will quickly scramble if they aren't heavily shielded. The actual physical work is performed by modular end effectors, specialized interchangeable tools located at the very end of the robotic arm. Depending on the task, the system swaps between simple clamping grippers, sophisticated bolt fastening drivers, or delicate component extractors. NASA's Restore-L mission serves as the blueprint for this capability, utilizing these end effectors for autonomous refueling and physical component replacement. Orbital robotics is a severe material science challenge. The software only matters if the hardware can physically survive the environment. But placing an autonomous robot in orbit demands an equally robust physical infrastructure down on Earth. This is a ground station, the terrestrial facility that maintains the vital communication link to the space asset. The primary interface is the parabolic dish, shaped specifically to focus scattered radio signals to and from the satellite. The physical diameter of the dish determines its gain, dictating its ability to capture weak signals crossing thousands of miles of vacuum. Because the satellite moves overhead at high velocity, these massive steel structures must continuously rotate to track it. Inside the facility, rack-mounted RF equipment, transmitters, receivers, and filters, converts those raw radio frequencies into usable baseband data. Without this highly calibrated physical ground architecture, the surfacer spacecraft is deaf. a billion-dollar robot immediately becomes uncontrollable space debris. That baseband data routes directly to the Mission Control Center, where specialized engineering teams monitor the operation 24 hours a day. They maintain contact using the TT&C subsystem. Beyond command and control, this link allows engineers to upload new digital logic to the spacecraft's onboard processors, modifying its functions mid-mission. Telemetry provides the continuous stream of sensor data required for this, reporting to health of the hardware and the software stack to enable regenerative updates from the ground. While AI handles the high-speed approach, delicate mechanical manipulation requires human-in-the-loop oversight to ensure nothing is accidentally broken during a repair. Operators physically execute these repairs from their desks, using bilateral control systems equipped with haptic feedback. Force-torque sensors embedded in the orbital arm measure physical resistance and transmit data back to Earth. The ground operator actually feels the tension of a bolt turning in space. Successful component repair relies entirely on this continuous, low-latency synchronization between orbital mechanics and human intuition. On-orbit servicing works because it merges three highly complex systems: autonomous rendezvous algorithms, ruggedized multi-axis robotics, and high-fidelity TT&C data links. Together, they change the economic math of orbital operations. Basic refueling services can extend a satellite's operational life by decades, a concept definitively proven by the MEV-1 mission. These servicing vehicles can also execute orbit modifications, capturing stranded spacecraft and towing them into correct operational slots. Crucially, this technology gives us a mechanism to safely capture and deorbit defunct satellites, actively mitigating the compounding space debris problem. Moving forward, satellite architecture will increasingly feature software-defined processing payloads that can be iterated upon via the command link. These regenerative architectures allow operators to dynamically adapt to market shifts, add new services, and optimize network performance long after the physical launch. To maximize this potential, future spacecraft must be designed from their inception as cooperative targets, complete with standardized grappling fixtures for safe, efficient servicing. By treating satellites as maintainable machines, on-orbit servicing takes the space environment from a static graveyard and turns it into a dynamic, sustainable, and upgradable network.